Bismillah ar-Rahman ar-Rahim. I welcome you to the 31st lecture for the series of lectures on advanced computer architecture. Today, the focus of our discussion will be the cache enhancement by reducing miss penalty or miss rate via parallelism and by reducing the hit time of cache. Today, after a brief review of what we discussed last time, we will discuss in details the reduction in miss penalty and miss rate via parallelism and reducing hit time. Last time we presented the 3 C's model of cache misses, which led us to the 5 different techniques. Out of these 5 different techniques, the 3 optimization techniques are large block size, which is usually used to reduce the compulsory misses, the large cache size, which is commonly used to reduce the capacity miss, and higher associativity, which is used to reduce the conflict misses. The other 2 techniques which we discussed last time were the wave prediction technique. This wave prediction technique checks a section of cache for hit first, and then on a miss, it checks the rest of the cache. Whereas the 5th technique is basically the compiler-based technique, which is usually used as loop interchanging or blocking for the optimization of cache performance. Today, we will talk about the other ways of enhancing the cache performance. These methods include reducing miss penalty and miss rate via parallelism, which is basically overlapping the execution of instructions with activities in the memory hierarchy. And the second method which we will discuss today is by reducing the hit rate to enhance the performance of the cache memory. Now, let us first of all talk about reducing miss penalty and miss rate via parallelism. The basic idea is to reduce the miss penalty and sometimes or miss rate by performing multiple outstanding memory operations through overlapping the memory activities and the instruction execution activities which take place in the processor. This can be accomplished by using 3 different approaches. The first one, known as the non-blocking caches, where this method is used to reduce the stalls on misses. The second approach is usually known as the hardware prefetching, which is used to reduce the number of misses. And the third one is the software prefetching or compiler-controlled prefetching. This method is also used to reduce the number of misses. Now, let us consider the non-blocking caches first. The non-blocking caches provide memory hierarchy similar to the out-of-order execution as used in the pipeline data path, which we discussed in our earlier lectures. For example, the instruction and data caches are decoupled to allow the central processing unit to continue fetching the instructions while waiting on a data cache miss. So this actually means that if during the execution of instruction there is a data cache miss, even then the central processing unit will continue fetching the next instructions. The non-blocking caches basically requires the central processing unit working on the principle of out-of-order execution. The non-blocking caches, also known as the lockup free caches, these caches allow data cache to continue to supply cache hit during a miss that is usually referred to as the hit under miss. So the hit under miss basically reduces the effective miss penalty by working during misses versus ignoring central processing unit's request. However, delicate situation occurs when multiple misses are overlapped. That is, the hit under multiple misses, or this is also referred to as the miss under miss. The miss under miss may further lower the effective miss penalty by overlapping multiple misses. However, an added complexity of multiple outstanding misses is that it is now possible for there to be more than one miss request to the same block. This I would like to explain to you with the help of an example. Here, let us consider an example with 64-byte cache blocks that could be a miss to address 1000 and then later on a miss to the address 1032, which means that within one block there are misses at two locations, that is the location 1000 and 1032. This shows that the complexity of cache controller significantly increases as in this particular situation the hardware must check on misses to be sure that it is not a block already being requested to avoid possible incoherency problem and to save time. This means that actually we have to design a complex controller to achieve the coherency and overcome the incoherency problems. The use of non-blocking caches can be beneficial if the memory system can service multiple misses, which may require multiple memory banks. typical examples of miss cache system is where it is used in Pentium Pro, and it allows up to 4 outstanding memory misses. Now let us see that how the average memory stall time is affected when we are using the non-blocking caches for handling the hit under miss and miss under miss, that is hit under multiple miss. For this purpose, let us have a look onto the graph that shows the average memory stall time for floating point programs and integer programs running on a system with 8 kilobyte cache using 32-byte block size and miss penalty of 16 cycles. Here, note that average memory stalls for floating point programs are relatively smaller, which is ranging from 39% to 76% as compared to the integer programs, which ranges from 78% to 81%. Also note that the floating point programs benefit from the complexity of hit under miss, whereas the integer programs, they get benefit from the simple hit under miss. This means that the non-blocking caches using miss under miss are though complex, but they are beneficial for floating point programs, whereas the simple non-blocking cache using hit under miss scheme is useful for integer programs. This is quite clear from the left-hand section of the plot, which shows that the percent average memory stalls for floating point programs are very low. Here, the percent memory stalls for hit under one miss is 76%, for hit under two misses is 51%, and for hit under 64 misses is 39%. That is, the miss overhead reduces with the increase in the complexity of the system. Whereas the right-hand section of the plot gives us the percent average memory stalls for integer programs, and it shows that the percent average memory stalls for hit under one miss and for hit under 2 up to 64 misses is almost same, and it is ranging from 78% to 81%. So from this, we can conclude that the hit under miss non-blocking caches can be used for integer programs without significantly increasing the memory stalls. Here, we have observed that the use of non-blocking caches reduce the miss penalty by overlapping memory accesses with out-of-order execution. Now, in order to further enhance the processor performance, another approach is used to fetch the items, that is, the data and instructions, into the caches before they are requested by the processor. This approach is known as the prefetch approach. This prefetch approach is implemented by using both the hardware methods and software methods. We will be, first of all, talking about the hardware methods to prefetch the instructions or data and reduce the overall miss in the system. The instruction prefetching is done in hardware outside the caches. Here, the hardware is designed such that on a miss, 2 blocks are fetched. That is, the requested block and a subsequent block. The requested block is placed in the instruction cache, and the extra prefetched block is placed in an instruction stream buffer. On a miss, the stream buffer is checked first, and if the requested block is available in the stream buffer, then following steps are taken. Number 1, the original cache request is cancelled. Number 2, the block is read from the stream buffer. And last, the next prefetched request is issued. Here, note that the prefetching relies on the effective utilization of memory bandwidth that otherwise would be unused, and that lowers the memory performance due to its interference with the demand misses. The researcher Jopi in 1990 made experiments with 4 KB direct mapped instruction cache and found that an instruction cache with a single block stream buffer catches 15% to 25% of misses, whereas the instruction cache with 4 blocks stream buffer catches 43% for stream fetching at different addresses and 50% at the same address. And the instruction cache with 16 block stream buffer catches 72% misses. The hardware prefetching technique also works efficiently for data caches to reduce the data misses. Here, the hardware identifies stream of accesses and then prefetches them in the data stream buffer. Thus, it allows to compute strides by comparing current and previous accesses. This has been observed in 1994 by Palacarla and Kessler, who considered the use of stream buffers for instruction as well as data for scientific programs, and found that the 8 stream buffers could capture from 50% to 70% of all the misses from a system with two, that is one for instruction and one for data, two 64 KB 4-way set associative caches. Now, in order to further understand the use of hardware prefetch caches, let us consider an example to see how the hardware prefetch can reduce the miss rate. Here, in this example, we want to find the effective miss rate of UltraSpark using prefetching and want to find how much bigger data cache would be needed to match the average access time if prefetch cache is removed. For this example, we will consider an UltraSpark 3 system which has got 64 KB cache and another cache of 256 KB, both having average miss rate per 1000 instructions equal to 36.9 and 32.6 respectively for 64 KB and 256 KB caches. Now let us see how we can solve this example. In order to solve this example, we assume that the prefetching rate is equal to 20%. Hit time is 1 clock cycle. The miss penalty is 15 cycles. And the data references equal 22%. And 1 extra clock cycle is to be used if the data misses the cache but are found in the prefetch buffer stream. Let us see how we can solve this problem. Considering the extra clock cycle for prefetching buffer, the average memory access time can be written as the miss rate for prefetch is equal to the misses per 1000 divided by the data references. Substituting the values given earlier, that is the misses per 1000 equal to 36.9 divided by 1000, and for 22 data references, the data references equal to 22 divided by 100, which results in a value equal to 16.7%. Whereas now, in order to calculate the average memory access time with prefetch caches, it is given by the expression as shown over here, that is, it is equal to hit time plus miss rate multiplied by prefetch hit time multiplied by 1. To this whole expression, the miss rate multiplied by 1 minus prefetch hit time multiplied by the miss penalty. Substituting the values corresponding to hit time of 1 clock cycle, miss penalty of 15 clock cycles, the average memory access time can be computed equal to 3.046. Continuing with, to calculate how much bigger data cache is needed, we have to find out the effective miss rate for prefetched 64K byte cache. This is given to be equal to average memory access time minus the hit time, whole divided by the miss penalty, and it results in a value equal to 13.6. Whereas from the given data for 256 KB cache, it gives us the miss rate equal to 33.6 divided by 22%, which results in a value equal to 14.8%. Now comparing these two values, that is the 13.6% for 64 KB with prefetch cache and 256 KB without prefetch cache, it shows that 4 times bigger cache is needed if prefetch cache is not used. Now, with this much discussion about the hardware prefetch caches, let us talk about the software prefetching technique to reduce the hit rate. This is an alternative to the hardware-based prefetching, where the compiler inserts special instructions to request prefetch the data before it is needed. Now, the use of this technique has got two typical cases. These cases are register prefetch and cache prefetch. Register prefetch deals with the loading of data into registers, whereas the cache prefetch deals with the loading data only into the cache and not to the register. However, there are a number of issues and limitations associated with the compiler prefetching. The first limitation is that the register or the cache prefetching can be faulting or non-faulting. The faulting prefetch may cause protection violation or an exception for virtual addresses, whereas the non-faulting prefetch does not cause protection violation or an exception for virtual address. Thus, it results in no operation in case of protection violation. The second issue associated with the software prefetching is that it is semantically invisible. That is, the effective prefetching does not change the contents of register and memory. Thus, it cannot cause virtual memory faults. This approach is made valuable by allowing the processor to proceed while prefetched data is being fetched. That is, the caches do not stall but continue to supply instructions or data while waiting for prefetched data to return. Furthermore, issuing the prefetch instructions take time, so care must be taken to ensure that the cost of prefetch issues is always less than the savings in reduced misses. Now, with this much discussion, to reduce cache miss penalty or miss rate via parallelism, let us summarize what we have said so far. We have described, in fact, 3 methods to reduce miss penalty or miss rate via parallelism. The non-blocking caches enable out-of-order processor to take advantage of more bandwidth behind the cache and allows several outstanding misses operating at once for programs with sufficient instruction level parallelism. Furthermore, the hardware and software prefetching techniques influence excess memory bandwidth for trying to anticipate the need for a cache. The prefetching generally reduces miss penalty, but it is started far in advance of the need, and it reduces the miss rate also. Having discussed 5 different techniques to reduce the miss penalty, 5 methods to reduce the miss rate, and 3 approaches to reduce the miss penalty and miss rate via parallelism, let us have a look at the final component of memory access time, that is the hit time, which affects the clock rate of the processor. Hit time indeed directly affects the clock rate of the processor. Cache access time limits the clock cycle rate. Hence, fast hit time has its importance beyond the memory access time. The 4 commonly used techniques to reduce the hit time are the small and simple caches, the address translation avoiding, the pipeline cache accesses, and trace caches. Let us discuss these methods one by one. And first of all, let us talk about the small and simple caches. While discussing the cache design, we have already observed that the most time-consuming operation in caches is to compare long address tag. This operation definitely requires bigger circuit for comparing, and as this circuit grows, the performance of the circuit becomes slow as compared to the smaller circuits. Thus, an obvious approach to keep the hit time small is to keep the cache smaller and simpler. A cache can be kept smaller so that it may fit onto the same chip as the processor is. This avoids the time penalty for going off the chip, and a cache can be made simpler, such as the direct map tag, so that the tag comparison can be overlapped with the data transmission. Let us have a look onto this graph to study the impact of cache size and complexity, that is, the effect of associativity and number of read-write ports. Here you can see that the data used in this graph is for 0.8 micron feature size, single read-write port, 32-bit address, 64-bit output, and 32-byte blocks for cache sizes ranging from 4 KB to 256 KB are shown. Note that depending on the cache size, you can see that the direct mapped, that is one-way associative cache, is 1.2 to 1.5 times faster than the two-way set associative cache. Similarly, the two-way set associative cache is 1.02 to 1.11 times faster than the four-way associative, and four-way associative is 1 to 1.08 times faster than the fully associative, except for 256 KB cache, which is 1.19 times faster. So from this, we can say that the lower associativity caches, that is, the simpler caches, have smaller hit time than the higher associativity caches, which are relatively complex. Now, considering the fact that smaller size caches are faster, the size of L1 cache has not yet increased on new generations of the computer from a very long time. The 16 KB L1 cache on Pentium 3 has actually been reduced to 8 KB cache on Pentium 4. Now, let us have a discussion onto the second technique to reduce the hit time, that is, by avoiding the address translation during indexing. This method is basically used with the virtual memory system, where small and simple caches are used as translation look-aside buffer. We will be discussing the design of virtual memory system in details in the next lecture. However, here I would like to say that the virtual memory system works such that the virtual address from CPU is translated to the physical address, and the physical address of the main memory is translated to the cache address. In virtual memory system, main memory is considered as another level of memory hierarchy, so two levels of address mapping are used. Now, if the address mapping is made such that the virtual address for the cache is used directly mapped instead of translating address at two levels, such a cache is known as the virtual cache, and the normal cache, which we have discussed earlier, is referred to as the physical cache. Note that using virtual cache, the address translation can be eliminated from the cache hit, as full virtual address can be used for both index as well as tag comparison. However, there are certain limitations due to which the cache designers do not always build virtual address caches. These limitations are: number one, protection. The page address for a virtual memory and the main memory is checked as part of the virtual address to physical address translation. However, what is a page address? This we will discuss in detail when we will be talking about the virtual memory system next time. The second limitation is regarding the physical address difference. In this case, every time a process is switched off, the virtual address refers to different physical addresses. This requires flushing of cache after context switch. And the third limit is known as the aliasing or synonymous. Here, the operating system or user program may refer to the same physical address for two different virtual addresses corresponding to two processes. So this results in having multiple copies of the same data. There are number of solutions to this problem. The hardware solution to the synonym problem is that we can avoid this by using two-way set associative caches. Whereas, while considering the software solution, the sum of the address bits can be shared. So, with this much discussion about this second technique, let us consider the third technique known as the pipelined cache access. We know that the overall cache hit time can be reduced by pipelining the cache access so that the effective latency of the first level cache hit can be multiple clock cycles. Hence, result is fast cycle time, which increases the bandwidth of the instructions. For example, the pipeline for Pentium 1 takes 1 clock cycle to access the instruction cache, and for Pentium Pro through Pentium 2 it takes 2 clock cycles, and Pentium 4 takes 4 clock cycles. This split increases the number of pipeline stages, which leads the greater penalty on mispredicted branches only. Now let us talk about the fourth method to reduce the hit time. This fourth method is basically using the trace caches. A challenge in multiple issue processors is to supply enough instructions every cycle without dependencies. We have already studied that one of the solution to this challenge is the use of trace caches. The trace cache is one which finds a dynamic sequence or trace of instructions, including taken branches, and it loads it into the cache block. This approach, however, facilitates to combine the branch prediction into cache with the instruction prefetching. This results in effective use of cache, that is, there is no wasted word on the conflicts. The conflicts are avoided as the prediction is validated along with the address to have valid fetch. However, it complicates the address mapping mechanism as the addresses are no longer aligned to the power 2 multiples of the word, which is the normal requirement for address mapping. Furthermore, the demerit of trace caches is that same instruction may be stored at multiple times. Now, with this much discussion on the hit time reduction techniques, we conclude our discussion on the cache performance optimization. You can notice that we have discussed 5 methods to reduce the miss penalty, 7 ways to reduce the 3 C's, that is the conflict misses, the compulsory misses, and capacity misses. And we have discussed 3 methods to reduce miss rate and miss penalty via parallelism. And at the end, we considered 4 techniques to reduce the hit time. However, we can summarize the performance of these methods with the help of this table. This table gives us the complexity level of each technique, which we have already studied, and we will give some comments also on the use of these techniques. For example, here you can see that the techniques used to reduce the miss penalty are having the complexity range from 1 to 2, where you can see that the multiple caches, which is an hardware technique, it is costly and it has got complexity level of 2, whereas the early restart and the critical word first technique is widely used technique, and the priority to read miss is a very trivial technique for uniprocessors, and it has got a very simple operational principles. Therefore, its complexity level is 1. Whereas the other 2 techniques which are used for this purpose are the merging the write buffer. This is used with the write through techniques, and the victim caches, they have got the complexity level of 2. The other 7 techniques which are used to reduce the miss rate include the large block size, which is a very trivial technique and it has 0 complexity, the larger cache size, and higher associativity. These are very simple techniques and they are widely used. Both these techniques has got the complexity level of 1, whereas the pseudo-associative and way-predicted, these techniques are relatively complex, and they are the pseudo-associativity technique is used in level 2 caches, whereas the way predicted is used in instruction caches. The compiler technique is used to reduce the misses, and this is basically a software-based approach which has got 0 complexity. The other 2 methods which we discussed, that is using the miss rate and miss penalty in parallelism, it can be used by using non-blocking caches, the hardware prefetching, and software prefetching. As we discussed just now, that these 3 techniques, they are quite complex and they are very rarely used. Then we discussed the techniques to reduce the hit time. The most widely used technique is where we avoid the address translation, and this technique is used with the virtual memories, and the trace caches, they are used in Pentium 4 processor. Now, with this much discussion about the optimization of caches, we will stop our discussion here, and next time we will start with the design and use of virtual memory systems. Till then, Allah Hafiz.